Now let's go for the Lewis definition. The Lewis acid electron pair acceptor. An acid accepts an electron pair. It needs an empty orbital to hold those electrons. Wait. Think of it as a hungry for electrons. So I have something that's hungry for electrons. It's an electron deficient. Remember, in case of Brønsted, we used to say proton acceptor. So I will remove proton and say electron, and instead of no, I used to say proton donor. This one is electron acceptor. And in the base, I will do the reverse also. In the base, I used to say a proton. Here I will say electron, and instead of acceptor, I would say donor here. So it is the reverse. Again, the acid is the one that accepts electron. It's hungry for electrons. It's electron deficient and wants to fill that gap. The Lewis base is the electron pair donor. It donates an electron pair. It has a lone pair of electrons ready to give. It as somebody who is rich in electrons. It has extra electrons and then gives them away. Let's see the example. I have an example here, says BF₃. So the BF₃ reacts with NH3 to form F3P NH3. That's a strange compound. How do you draw or write down this compound? Here, the BF₃ is the Lewis acid. The boron trifluoride is the electron deficient. You remember that we said the boron can only accept 6 electrons, right? Around it, incomplete octet. So 1, 2, 3. So it has an empty orbital waiting for electrons. It wants to be an octet. So it can accept the electrons pair from the NH3. The NH3 has extra electron. It has a lone pair of electron on this end. So it can be an electron donor. So this means that my NH3 is the base. This is my base, that one that has the extra electrons. So it is an electron donor. And the one that's electron deficient, the BF₃, that one needs the electrons. So it is the electron acceptor. So it is the Lewis acid. Please focus. Some of the students ignore the Lewis acid and base definition. I don't know why they focus only on the Brønsted and on the Arrhenius, but the Lewis also comes in the exam. Ammonia has lone pair of electrons. It's giving it to the BF₃. So they form a coordinate covalent bond. Usually there is a coordinate covalent bond in the Lewis definition. Why is that? Because the coordinate covalent bond is a bond that's made when one of the substances don't have enough electrons to share. So it's actually the normal covalent bond is done when every atom shares one electron. So this one shares an electron and this one shares an electron. If one of the substances or the atoms, ions or atoms or molecules that make the covalent compound or the covalent bond doesn't have enough electrons, like the BF₃, so it still wants to make the bond, but it has no electrons to make the bond. So the electrons are all coming from one side. The NH3 has an extra electron. So here, this is like a beggar. He wants to make the bond, but he has not enough money to make the company. So the company is made by the money of the NH3 alone. This is famously known as the coordinate covalent bond. Coordinate covalent bond. So there is a sharing of electrons, but the electrons are coming only from one side. That's why you usually draw an arrow here. So just to remind, the BF₃ always that the electron that was used to make this bond is both of them coming from the NH3. So the reaction, NH3's lone pair fills BF₃ empty orbital. Boom, acid-base reaction complete, no protons transfer, no water involved, pure electrons transfer. Why Lewis is the broadest definition? Let me see and make a comparison. The Arrhenius definition happens only in aqueous solutions and covers H plus and OH minus only. The Brønsted-Lowry covers the proton transfer and any proton transfer reaction. But the Lewis electron pair transfer, everything, proton transfer, non-proton reactions. Lewis explains all the Brønsted-Lowry reactions because proton transfer involves electron movement. plus reactions like BF₃ plus NH₃, where no protons move at all. So we cannot explain. So that's why it's mandatory. It's not an optional definition. Because with the Brønsted-Lowry, I cannot explain Fp3 and H3 because there is no proton move. This is an acid and this is a base. I don't have a proton that move from Fp3. There is not even a proton in the BF₃ structure. So how you will explain with the Brønsted? So now the question is when to use everyone. I will use the Arrhenius simple aqueous acid base reaction, most introductory problems. Use Brønsted-Lowry when there is proton transfer reaction, any solvent, amphoteric species. Use Lewis when there is non-proton transfer reaction, electron-deficient compounds like BF₃, AlCl3, etc. So the exam strategy, if you cannot identify an acid-base pair using Arrhenius or Brønsted, default to Lewis and ask yourself, does one species have an empty orbital like an acid? Does one species have a lone pair like a base? If yes, you have got your answer. A very famous example is actually the hydronium ion. When the water molecule takes a proton, it forms a bond with this proton by a negative covalent bond because it uses this lone pair of electrons to make the bond with the proton. The proton, when it comes to the bond, has no electrons to make the bond. It's just a proton. So in order to make a bond, it makes a negative covalent bond with the lone pair. So I can say that the OH here has donated a lone pair of electrons. That's why the electron donor is the Lewis base, and the proton itself has accepted the electron pair, so it is a Lewis acid. I don't. If I want to say this by Brønsted, it will be strange to say that the H plus gives an H plus to the H2O, but actually that's what happens.